is very preliminary work on inlining, and so this is work with my my graduate student. So, oops, sorry. So this audience doesn't really need too much education on what inlining or why we would inline, but so in particular, Smalltalk is very relevant here. So Smalltalk is full of sends. There is nothing in Smalltalk other than assignments and return other than sends, and so sends become really critical. So we want to inline to obviate the need for those. Access variables more efficiently. And in modern architectures, there are lots of registers. And if your methods are all very small, then you're not using most of those registers most of the time. So, and larger bodies of code obviously create more optimization opportunities. So there's kind of a hierarchy of need for inlining. So C compilers, for example, people inline, but it's not that critical because all of the calls, apart from function pointers, are essentially direct branches. So the hardware can do its look ahead, and there is no slowdown in calling a method, or very little slowdown in calling a method. Essentially just have to save the return address. Then we go to languages like Java or C++, where we have vtables, but they're static. So most of the calls to methods will incur a slowdown because there's an indirect branch, and that indirect branch will stall the look ahead, but otherwise they're relatively straightforward. But then we get to dynamic dispatch, which is Java and interfaces and dynamic languages. And here not only do we have the pipeline stall of the indirect branch, but we also have the slowdown of doing the calculation for the send or the call. So Smalltalk is dynamic, and so it has all those dynamic dispatch problems, but it also has some are social aspects, like very small methods are encouraged and the hierarchy is heavily used. But there's also fundamental aspects, which are that there are no control structures in Smalltalk. Everything is a message send. So control structures are message sends just like everything else. And also, Smalltalk has non-local returns, which is a very rare construct, but they are used fundamentally in the control structure. So this is very critical for Smalltalk. I won't go through the dispatch mechanism. It's what you'd expect, but there's we go up the hierarchy trying to find the appropriate method, and then we dispatch to it. So this is the same as Java, except in Java, because it's a statically typed language, the decision about whether something's going to be does not understand, i.e. a syntax error or a semantic error in Java, and the offsets are all statically determined. So in Java, when you send a toString message or call, that's in object, which means it's going to be at a fixed place in the dispatch table, the vtable for whatever class. So this makes it relatively fast. You incur the pipeline stall of the indirect branch, but otherwise it's very, very fast. So there's lots of work been done on this. Deutsch-Schiffman dispatch has been used since the 80s. And what this is that there's a bunch of special control flow selectors. So if true, if false, if nil, if not nil, etc., while true. And these are all important because there is no control structure in Smalltalk, and so it really matters that these operations be recognized. And so those are actually compiled by the compiler not to be sends, but to be explicit code. And the problem with that is, to be semantically pure, you have to handle something, especially when it isn't actually one of those. And so that complicates things significantly. The other problem with it is it's only specific things that are handled that way. So everything else we have to inline in a more general way. And caches are the way that this gets resolved. And so polymorphic inline caches have been in use since the 80s, and particularly heavily used in Self and subsequently JavaScript. And Self and JavaScript have per target dispatch tables. So in other words, when you have a particular structure that in JavaScript and Self essentially gets compiled into a class, sort of a hidden class, and then the sends to that class are going to be compiled for that class directly. This isn't traditionally done in most Smalltalk systems, although it is in the Smalltalk system that we're working on. And inlining is almost exclusively handled with native code JITs. So when people talk about inlining, they're thinking about native code JITs. What's new in Zag? It's a new Smalltalk implementation. There's a bunch of reasons why we're doing this, but one of the aspects of it is we have two execution models. One is the threaded execution model. This doesn't mean hardware threads. This means indirect jumping. And that's used for debugging. And then we have native implementations for speed. And the transition between these is seamless. So you can be in the middle of something you have to debug. You can be executing native code. And when you start the debugger, it basically says, when I return from this, I will be in debug mode, and so we can stay in debug mode as long as we want. So we want these two versions to be semantically the same so that we can actually debug the code. So we compile methods to concrete classes just like Self and JavaScript do. So what this means is that Self and Super are exactly known in most cases. So that means that when we see a send to Self, we know exactly what that is. Whether the corresponding method is above us or in this class, it's going to be compiled for this. The Zag model is what I call on-demand compilation rather than JIT, because in my mind, a JIT compiler will look at, as you've just heard, all the sort of context that's available in the VM at the point that we're compiling, rather than, in our case, we're just looking at the receiver of the message. So when we're compiling it, it's compiled for a target class. And there's a version of tiering here. So we first of all compile for threaded version with no inlining, and then we can do various other alternatives after that. So inlining. First is we have no ad hoc selector inlining, so if true or false, not handled specially. Inlining is semantic. In other words, it happens entirely at the intermediate level. And so it's debugging and the native are the same code. We do inlining breadth first, so basically we have our intermediate and then we go looking through the current version of the intermediate for opportunities, inline, etc. And this means that we can be more intentional. Because we're doing it at the intermediate level, there can be more intentional about the inlining. And so we can filter this in various different ways. First is we can do n breadth first inline passes. We could maximize the number of inlines that we're wanting to do to minimize code or manage code explosion. We could also do things like inlining until all the block closures have been inlined that are possible. So that would get us most of the performance. So now we'd be back to a language more like JavaScript, I guess, in that the data structures will all actually be in code rather than in sends. We could also inline just code that had block closures as parameters. And we could also do incremental inline. So we could inline partially, sort of referencing the previous talk, inline partially, and then at some later date say, okay, it's worth doing 3 more rounds of inlining to get optimum code. This is actually the focus of the paper as I originally submitted it, which was the various opportunities to inline. Most of these are fairly typical. The most interesting one, I guess, is the 4th one, because Smalltalk doesn't have any loop structure. So traditional Smalltalks handle that by recognizing while true and a couple of others as, oh, that's a loop, I better translate it that way. But what we do instead is we recognize tail call recursion, so, or tail calls generally. And so if when we're inlining, if we have a tail call that is to something that we're currently inlining, then we turn that into a branch. So this means that we don't have to have any special handling whatsoever to handle loops. We just have tail calls. And the fourth or third from the last one, if it's a value message, then basically we're just going to inline the block closure at that point. Conclusions, there are advantages to semantic inlining, and we don't have any execution benchmarking results yet. We will at some future point, at which point we'll come back and report this. And Zag Smalltalk is, oops, actually that's the wrong, that will send you to the wrong place. Sorry. We moved it. So it's Zag Research. So if you just go to Zag Research on GitHub. Sorry about that. So any questions? Oh, I should mention my university is hiring, my department is hiring. We have lots, like 8 open positions. They won't all be programming languages by any means, but if you are a PhD student or you have a PhD student who's about to graduate and would be interested in teaching in Canada, send me an email.
I was puzzled about how, supercalls are always static, but self is usually dynamic. How can you make those precise?
Sorry, because we compile for a particular class, so if we were compiling, I don't know, anyone, for example, which is a message that extracts just a sample value out of a collection. So the default version of that just actually uses do and returns the first value it finds, but there are subversions. So if you had a subclass, actually that maybe isn't the best example. If you have a subclass of something negated, okay, there's a simpler one. So if you send a message to a small integer to negate, or negated, it will actually, the code is actually in integer. It's not in, or it's actually in number. It's not in small integer. So it will be compiled into the dispatch table for small integer. So it'll be compiled, and now we know that that is self. Self is small integer, and so any reference to it we can handle. And also, if you, it's very common in Smalltalk to have virtual methods that send messages to self, but those are being compiled for the target class, so we'll actually have the right self in all those cases.
Thanks. Follow up on the previous question. So does that mean that you're specializing basically for the target or for self? So basically an overloaded or like an inherited method that it's inherited in a class chain of depth n will have n implementations?
No, we would have it just for the ones that you actually sent messages to. So what happens is we start off with empty dispatch tables. The first time you send a message to a particular class, we see it's not there. We go off, we find that, we go through the semantically appropriate thing to do that, and then we compile it for that class. And so now everything is known about that. In that compilation, everything is known.
Right. Okay, thanks. So question on the tail call optimization. So basically, so that it seems like you instead of tailoring or like looking for specific known control structures, like if I implemented my own bespoke control structures in Zag Smalltalk, I would get like the native performance, let's say, of a while in a classical Smalltalk.
So because there are no ad hoc selectors, you get maximum performance regardless of.
Right. And do I get sort of? I mean, these performance comparisons are the same kind of performance as with the sort of the hand-rolled optimizations for while loop and such?
Yes, exactly. So we actually rewrite while true. If you look at most Smalltalk implementations, they just say while true because they know that it's actually going to be compiled somewhere else. The only time you'd end up there would be if you did a perform. But for us, while true is rewritten to be a tail recursive implementation, as is one to or to do, for example, in small integer.
So the lazy specialization seems like really cool. Does that mean that if you update a method, you have to effectively empty the vtable of that class?
Track of all of the compiled code that knows about this implementation. So if we change something way up in the hierarchy, yes, lots of methods could be, but we just remove from the vtables, and then the next time the message is sent, we'll recompile it.
Do you also de-optimize them on the stack too?
No, they don't exist on the stack in that sense.
So if you have
I see what you mean.
Yeah, you have a specialized version that's executing.
No, we haven't thought about that. Perhaps we should.
Okay, we're pretty much have time, so let's thank the speaker again.